So I will present work on larger scale. We discussed so far on Milky Way. Now let's move to galaxy clusters, and I will try to discuss recent work that we have done to present to discuss the distribution of dark matter in galaxy cluster using as proxy the X-ray and the Sunyaev-Zeldovich effect. So galaxy clusters are the end products of hierarchical structure formation. They are dark matter dominated, and they represent a sort of closed box representation of our universe, conserving the ratio between the baryon mass density and the total mass density. And this ratio is represented by the gas mass fraction that we can measure directly in galaxy clusters. They have been also used recently to probe the level of a collisionless nature of dark matter, as shown in these three examples, starting from a very famous bulk cluster up to several objects that were found more recently, in which the dark matter has recovered from the gravitational lensing signal originated from the background galaxies is here represented in purple, and the hot gas, the one resolved by X-ray emission, here is in red. And the level of collisionless is represented by the displacement, relative displacement between the hot gas and the dark matter distribution. We know that the hot gas is collisional, and indeed the fact that this mismatch is in the order of few 10 up to 100 kiloparsec is telling us something about how much not collisional is the dark matter. Sorry, but I need to go through this because apparently it doesn't work properly. So what we are planning to do is using X-ray, basically XMM observation of a galaxy cluster, combined with a resolved signal from the Planck satellite that provided direct information on the integral of the pressure that we can get from the ICM, and we combine with X-ray that provide instead the measurement of the density, because of the process that we observe here is mainly Bremsstrahlung emission, so it's driven by the density square of electron and protons here distributed in the plasma, times and the temperature, that is a spectral measurement that we can get directly from the distribution of photons as function of energy. This is for the coma cluster, and we know that there are strong indications that the combination of this quantity can provide indeed oh dear, it's getting better, worse and worse. Okay. Can provide a directly measurement of what the accretion around in a dark matter halo happen. This accretion occurs on scales that cover up to tens of megaparsec, and we know from hydrodynamical simulation, as represented here, how this accretion is expected to occur from the regional fluctuation in the density field. The problem that we have now is the fact that we are not able, with present X-ray and also with SZ data, to cover up to a few times R500, but we are limited to the region within R200 that describe the virialized structure of galaxy clusters. So what was the purpose of our project called XCOP was to make a dedicated exposure of nearby massive system to look to the emission, to resolve emission up to R200, and combining this emission with a Planck measurement of a few times R200, the idea was indeed to try to recover all the thermodynamical properties of this quantity, and then by combination of these thermodynamical quantities to recover the total mass distribution in this system. These are 12 objects. You see here represented the image in X-ray and overplotted the contour plots of a Planck signal. So we can recover the density, the azimutally average density, temperature, and pressure. Basically, density and temperature are independent measurement coming from X-ray, whereas the pressure is a quantity that comes from the Planck measurement. And through the combination of this quantity, applying the perfect gas law and with the static equilibrium equation, we can recover the total mass distribution, so the total mass resolved as functional radius for these systems. Basically, what we do is we use the density profile, we use different mass model, for instance, a Navarro-Franken-White or an isothermal mass model, and then we recover, we invert this quantity we invert the hydrostatic equilibrium equation, and we infer which is the temperature and the density or the pressure for this system. And then we apply a likelihood that combine all this information to constrain the parameters that describe the underlying mass models. Doing this in a paper that we presented last year, we probe for our system a different mass model, and we probe that most of our system prefer the Navarro-Franken-White description. Here is represented the bias factor that is just the difference between the bias evidence that you infer for a given mass model with respect to the best mass model. And all the red points here represent a Navarro-Franken-White mass model, and basically all the colored mass model are excluded at very high significance. And in particular, we were able to get this constraint at very few percent statistical uncertainties. That has been a very big success for this kind of project, being one of the best constraints that we can get through hydrostatic equilibrium equation in galaxy clusters. I represent here for all the system the relative error on the mass model at a typical overdensity of 500 times the critical density of the universe that define the region that are more relaxed in a galaxy cluster. We measure the statistical error of a mass profile is in the order of 5%. Now we are extending this analysis, including a more detailed reconstruction of the mass model, in particular in the inner part, including also the effect of brighter cluster galaxies and also from satellite galaxies, and applying more properly the projection of the signal in the very inner part, meaning within 10 kiloparsec or so. And these are work in progress. You see here the reconstruction of the density, temperature, and pressure. Here the gas fraction that I was mentioning at the beginning. You see this is in gray is the predicted omega B over omega matter from cosmological parameters. And as I said, the galaxy cluster, at least massive galaxy cluster, are a closed representation of the universe. And indeed, we are able to recover almost all the baryon budget in this system. On the left here in the panel, this corner plot just represents the constraint that we can get on the Enasto mass profile, putting a very interesting constraint for the first time in galaxy cluster on alpha or mu. That is one of the parameters that characterize the steepening of the Enasto profile in the very inner part. Also, we investigated some different models, because this is in the dark matter context has been what I explained so far. There is also a growing evidence that some attempt had to be tried to reconstruct the mass profile using just the baryon that we observe directly, both in galaxies and in the intercluster plasma. And we also try to recover the gravity that we measure using both of the MOND, so modified Newtonian dynamics, or also the emergent gravity paradigm that was suggested by Verlinde a few years ago, in which basically we live in a dark energy dominated universe with ordinary matter that produce just perturbation, and that induce an emergency of effect, gravitational effect that we can identify as dark matter, and that can be also measured properly for a static, isolated, and spherical symmetric system. That is basically the assumption that we regularly do to treat galaxy clusters. So given the baryonic distribution and given a measurement of Hubble constant, we can recover the dark matter, the apparent, the emergent dark matter profile. And the same can be done also for other laws from modified gravity. And the results, once compared with a hydrodynamical mass profile, is encouraging for some scale, but definitely not over all the scale that we observe, meaning that the gravity in general is particularly weak when you try to explain this gravity only using the baryons that you observe, in particularly on scale in the inner part of galaxy cluster, let's say below 1 megaparsec. And once you move at R500 or R200, the match is more encouraging, but definitely suggesting that probably there is also a dependence on a scale that is not treated properly in these alternative gravitational scenarios. How much is left? Because going through this but anyway, if you can try also to from a more astrophysical point of view, you can try to infer which is the non-time aperture support that could play a role in making equilibrium in your systems. And in this case, just assuming that the baryon fraction is indeed the one that we assume from cosmology, we can infer that the role of non-time aperture support, like turbulence or bulk motion, that still should be present as a kinetic energy in the plasma, is in the order of between 5 and 10% in all the massive systems that we are investigating here. So what next? Next is a project that started a few years ago with an Heritage XMM-Newton program that will be 3 megaseconds of XMM-Newton time dedicated to observation of 118 Planck selected objects. This is a sample that is 10 times the ESCOP project, that sample that I described before, and also covering a larger mass, and in the luminosity distance a factor of 10 more extended. So if ESCOP was limited to do very massive nearby system, the Heritage sample cover up to ratio 0.6 and down in mass a few times 10 to 15 solar masses. And I just can conclude now just presenting the first gallery that we have produced in a paper that we submitted to Astronomy Astrophysics, in which we present our project that was renamed Checkmate for a cluster heritage with XMM, and to study the mass accretion and the thermodynamical properties and endpoint of the structure formation. And the idea indeed is to probe the mass distribution for all this system, because the idea was indeed to get an exposure that allow us to recover the mass up to R500 at very high significance, and to expand the work that we did with ESCOP to get more information about the mass distribution in this system. Thank you.